Hello everyone, welcome to today's presentations on Project 1 Memory Hierarchy Designs on the subject of Advanced Computer System and Architecture. My name is Lee Kong Ming, and together we also have Gunawati as well as Wong Wei Yi to present on this title today. So this is the agenda for today's presentations. We will briefly talk about the memory hierarchy foundations with software behavior profiling, memory technology analysis, SRAM, DRAM, and flash, advanced cache optimization, XERAM power consumptions reduction, and last but not least, the case study on i7 Intel Core versus the ARM Cortex-A53. So I will pass the time to my friends Gunawati. Thank you.
Thank you, Kong. Let me start my presentation by explaining the memory hierarchy. In a computer system, memory is arranged from the fastest but smallest at the top to the slowest but the largest at the bottom. This includes register, cache levels, RAM, and secondary storage like SSDs. The purpose of this hierarchy is to balance speed, size, and cost. Higher levels are extremely fast but expensive, while lower levels are cheaper but slow. A very important principle here is locality. Temporal locality means data that was recently used will likely be used again, and spatial locality means nearby data will probably be accessed next. This principle allows cache to work efficiently and speed up the program execution. Okay, next, cache performance. Cache performance depends heavily on how our programs access memory. For loops, accessing data sequentially improve spatial locality. Arrays, for example, run faster when accessed row by row instead of column by column. Recursion may increase stack usage and affect cache, while too much branching can cause mispredictions and slow down the pipeline. To demonstrate this, we ran a simple profiling example using array stride access. Stride 1 gives the best performance because the elements are accessed in order. When the stride increases, the CPU starts skipping more cache lines, causing more misses and slower performance. Next, about the memory technologies. Now, let's look at the three main memory technologies. SRAM is used to cache memory. It is extremely fast because it uses 6 transitions per bit. It does not require refreshing and is ideal for L1, L2, and L3 caches. The second is DRAM, which is our main memory. It's slower, needs periodic refresh. It uses rest and cache signals to access rows and columns inside the memory banks. If multiple accesses hit the same row buffer, it becomes very fast, but random access slows it down. Third, flash memory, found in SSD, is slower than RAM but faster than hard disk. It is non-volatile and good for long-term usage. Sequential I/O on flash is very fast, but random I/O can be much slower. Next, the impact of the access patterns. To conclude, different memory access patterns have a different impacts on performance. For caches, sequential access increases hit rate while random access causes more misses. For RAM, accessing the same row repeatedly gives row buffer hits and better speed. And for flash memory, sequential operations are much faster than random reads or writes. Overall, understanding on how memory works from cache to RAM to flash help us to write the software that runs faster and uses hardware efficiently. Even simple coding choices like a loop order or array access can significantly improve performance. Thank you.
Thank you, Gunawati. I'll be explaining on why advanced cache optimization required and the key techniques to reduce heat time and store time. CPU speed grows fast, but DRAM doesn't change much. If we are using normal cache, CPU will require to waste power on waiting. There's total 10 advanced cache optimizations distributed into 5 categories. I'll be explaining each of the category on one examples, according to the lowest cost and also complexity. Small and simple L1 cache. L1 will be fast due to it will be following the computer CPU's speed. Small L1 shorter critical path, best with array loops and repeated variables. Second, merging write buffer. It will be allowed to combine adjacent writes so that fewer DRAM transactions. If multiple small stores can cause repeated DRAM activation, it will be more expensive. Used with graphics and image processing. Third, critical word first. Fetch the required words first, not the whole block. Array list start, so like CPU will resume as soon as critical word arrive. It will help to reduce the miss penalty, even although like the actual memory doesn't change. Next, both of this is the higher complexities and also cost. Non-blocking caches. CPUs, this non-blocking cache CPUs allow continuous on hits even if like miss outstanding. This will help to increase the cache bandwidth by using the miss status handling register to improve the 9 to 12.5%. Work best with the high instruction level parallelism. Lastly, compiler control prefetching. Compiler will insert a prefetch so that it will be fetch the data before needed. It will be best using with matrix multiplication prefetch next block. Next, I'll be continuing with what use power, why is it matters. For the four important sources of SDRAM power, synchronous dynamic random access memory. First, static power. It will require always on, baseline power just to keep DRAM powered and clock running. Lower voltage generation, DRR2, DRR3, DRR4 will reduce the static power accordingly. Next, dynamic power. It will be used when row activation, read-write pre-charge. Row activation will be the highest energy cost. Next, refresh penalty. It will be required to refresh every millisecond. Higher, bigger DRAM, it will be require more refresh energy. Lastly, bank level energy behavior. It will be cheap when good locality, so that fewer row switch row, then less activation energy. Lastly, on my part, I'll be explaining on hardware and software technique to reduce the DRAM power. Wattage scaling. It will be reducing the wattage based on cutting power dramatically. Power down modes. Whenever DRAM can sleep, it will be save energy. Third, row buffer management. It will reorders the memory control to maximize row hits. Fourth, banking. It will be only activate the required portions for DRM. Lastly, using cache. Larger and smarter cache hierarchies reduce all the DRAM work. Next, on the software behavior side, it will be improved locality, use loop blocking to link, sequential array access, and also reusing data close in time to increase the row buffer hits. Second, reduce the random access. We'll be preferring the arrays over linked list, cause unpredictable row jumps. Not the last is the batch memory activities. It'll be most effective when we're using long continuous bursts so that lower activation costs. Lastly is increase the cache hit rate. If like fewer DRAM access, then we'll save a lot of energy.
Hello, I'm Ming. So I will continue to talk about the case study Intel Core i7 versus Cortex A53. So i7 has a significantly larger and different cache hierarchy compared to the A53. i7 is built for high throughputs. It has a L1 cache of 64 KB total, L2 cache of 256 KB, L3 cache of 8 MB shared among 4 cores, while A53 is built for the efficiency. It has L1 cache, which is configurable, and L2 cache, which is optional and configurable shared cache, but it does not have L3 cache. In memory bandwidth aspect, i7 uses a dual-channel memory controller like DDR4. It has a maximum theoretical bandwidth of 34.1 GB per second, while A53's bandwidth varies greatly based on the SoC implementation. That is to say, the bandwidth of A53 depends on the SoC choice by optimizing the power and the cost. Next, we have the DRAM access behavior. i7s use an out-of-order execution model. It aggressively hides the latency through reordering and speculation. This is to say, when a cache miss occurs, there will be still another independent mode to execute while waiting the memory to arrive. and it uses an advanced prefetching. For A53, it's using an in-order execution model. It stores pipeline into the data returns from memory, and it uses a simple prefetching. So the typical software workload of these two processors are i7 is used for the performance and high throughput. So it's suitable for heavy desktop application, gaming and data analysis, while A53 is used for power efficiency and sustained operation. It is best for mobile apps, IoT tasks, as well as the background processes. So the key takeaway here is there's no which i7 or A53 is better, but we need to choose between them based on your workload and constraint. If you are going for high throughput, irregular, and latency sensitive data, you will choose i7. If you're going for efficiency and good enough for certain purpose only and optimizing the cost and power, you will go for A53. I think that's all for our presentation today. So thank you for your time to participate in today's presentation. And I hope that you really learned something new from our presentations and appreciate the times of you with us today. Thank you very much. Bye bye.